The problem that we're going to be attacking today, this question, Seborg 17.8. Now, the dynamic temperature sensor, right? So they tell us there's some kind of thing called the temperature, which is being measured by an analog probe, right? And they tell us that there's a transfer function that we know which relates. What they tell us, so there's this temperature, and they tell us that there's a transfer function that we have that they just give us. So we have a 2-second delay, and we have kind of first order dynamics in this temperature sensor. And then they tell us that this actual temperature, so this guy over here, undergoes a kind of a pulse input. So they tell us that it starts out at 70 degrees Celsius, and then at time 0, it goes up to 85. It then stays there for a while, and then at time 10, it goes back down to 70. Right? So this is what they tell us. This is what they tell us about the situation. Now, I think I've said this before, but I think the key to understanding how these problems work, or kind of to check yourself when you get answers, is to make sure that you have a really solid image in your mind of how this response, what that response should look like. So before we draw in any discrete elements, I'm just going to draw in my sketch version of what this response is going to look like. And there's a couple of kind of assumptions built into this. So I'm gonna draw in slightly fainter color. I'm just gonna, so that we have some kind of a guide to go for. I'm gonna draw this pulse. So that's the real temperature, and then I'm gonna just draw what I think is going to be the response of Tm. And we know the first big assumption is that, as with all of our problems in this module, up to time 0, nothing has happened. Okay, so when they tell us that the original temperature was 70 over here, and what they really mean is it was 70 and it has been 70 for all of time, which means that the measured temperature has been equal to that 70 for all of time. And so the only change we expect is at time 0, right? And we know what a first order response looks like. A first order response looks like this. I'm just going to sketch that in. Now, I haven't drawn it to scale because when you actually work out the problem, it's actually, I think, one of the lessons that you learn in this problem is that even though there's a quite a large temperature difference here, right? So there's about 15 degrees of difference, right? The measured maximum, which we expect, if we sketch the rest of this out, we expect this kind of first order doublet behavior, right? So what that means is there's a first order response up, and if that were just a step, that would be very simple. It would eventually arrive at that value, but because there's another step down, it doesn't actually get all the way, and it starts stepping down immediately at that same value, right? So it stops stepping down as soon as the input starts going down. And the lesson is that we measure a lower maximum temperature. If you think about why we're being even asked this question in the first place, is like part of the problem is, well, there's a delayed response. And then there's a second problem, which is now why we're in this part of the module, is that they tell us that this is sampled, right? And I'm going to use my same convention that we've been using throughout. We actually end up with a sampled version of that. And the sampled, or the sampler rate, every 2 minutes, right? And that's, in my mind, let's say, obviously wrong, because the units that they've been using in the rest of the question is seconds. And so the problem that I'm going to be solving is actually the problem for 2-second sampling, right? And so there's a 2-second sample over here, and every what we can see is that the kind of scale of the 2 seconds is within the kind of scale of what we expect the response to be. And I'm just going to draw the points. I'm going to highlight the points at the sampling points. What we can see is that this the sampling rate is actually it divides cleanly into the times at which things happen. So that's the first thing that we notice. The other thing that we notice is that this input can be kind of modeled as step signals. That's going to be important a little bit later. So just keep that in mind. And so the values that we would write down, remember, I kind of have this way of thinking of discrete signals as being the values that you would write down if you were to tabulate this in a spreadsheet, right? And so we would write down these particular values of Tm, and we would write down a value at 0 seconds, 2 seconds, 4 seconds, and so on, right? So we've got a set of times, and those times are these discrete times, and we'd have a value, if we are talking about the deviation version, which is kind of what we would calculate, that would be 0, but we also know that there's the actual value, that's deviation. And that's actual, right? So the actual value is obviously 70 degrees higher than the deviation variables, right? Because even though the problem tells us we start at 70, to do this problem using the math that we do, we need to subtract that initial value to get into deviation variables, do the math, and then that means that we have to add it back on when we report the value. So that I have at this point done 0 calculations, right? So I'm kind of thinking about this problem, and I'm looking at the time constant. How did I know to draw the diagram the way that I did? Because I'm looking at this time constant over there. That's an 8-second time constant, right? So if we were to just draw in scale, if we know that a step response of a signal with a 8-second time constant will only get like 63% of the way at 8, right? And so if we're talking about a thing that then at that point starts going down again just after 8, clearly we're not reaching that point, or even close to that point. If you have this picture in your mind, that we are working with a continuous signal, what we actually have is a continuous signal. It's not some kind of a reconstruction. It's a real continuous signal. There's a measured signal over here, and then we simply sample it. And so once you understand that, you understand that the nature of this response is the correct answer is, if we've done the math right, that the dots will lie on top of the line. In other words, we will find values that exactly correspond to the continuous version of Tm at each one of the sampling points. And I think that's the most important part of understanding how to check yourself, is to understand what to expect when you think about what the answer will look like. Now, I asked you to solve this problem in a more extensive way than the original wording. So at this point, we're almost done, right? The original problem just said, simulate the system and find the maximum value, and you could basically just go and say, okay, well, I plot the value, I look at the maximum value, and there you go. And I'm going to walk you through the 3 different ways in which I asked you to solve this problem. So just to remind you, I asked you to solve it symbolically. And so let's say analytically. I asked you to solve it by simulation. And then I asked you to use the Z transform. So, right, so let's get the first version of this out, because that's the easy version. How do we solve this analytically? We do our classic version. This is actually a problem that you could solve in CPN, which is that we're going to take the Laplace transform of T, of t, right? Which is now this function over here. And we can recognize that that's going to be a step up followed by a step down with 10 seconds of delay, which we're going to, so in other words, it's going to be 15, which is the size of the step, times 1 plus that, 1 minus that delay term, times our good friend, the step input. Okay, so that is the Laplace transform. That means we now have T of S, and we know that Tm of S is equal to T of S times G of S, right? We then calculate that, and we then inverse the Laplace transform. Okay, to obtain Tm of T. Now, we had a lot of confusion about, so, okay, but what's the analytic version of the sampling now, right? And the analytic version of the sampling, let's say, I think a lot of people are confused because it's so simple, because they expect there to be more to it. But actually what you have is, once you have this function of time, so this will be some kind of thing that's got times in it, right? All you do is you take this time and you plug that in to the formula, right? You evaluate the formula and you write down the number that you obtained in that result. That is what sampling corresponds to. And so there's actually nothing more. There isn't a specific function that does this, or that you need to use. You can just use it manually. You can just plug in the values yourself. You could even copy this formula into Excel, or you could use Lambdify in SymPy or whatever, and you could do that no problem. Now, because of the weirdness that often results in SymPy, I'll show you now that I've kind of resorted to a little bit of a special function which I've written into TB control, because you get some interesting results. Okay, so here's that whole analytic question solved. Okay, so let's go. Let me just also make this a little bit bigger. So I've just encoded a couple of codes here to show what the steady state value was, what the step size was, and so on. And you'll recognize all the same functions that I had from the drawing earlier. So you can see, you should recognize there's a very strong similarity over here. So we've got, there's now our deviation version of Tm, right? And the actual version is simply the deviation version plus that value. Let's just see what that actually looks like. And so a lot of people will be looking at this and saying, well, you know, this is kind of like a useless version. A lot of people are saying, oh, what's this gamma? What's this theta over here? We've come across these guys before. They shouldn't bother you too much, because like the thing that we are trying to do is unaffected by whether we have nice values for this. And as I've mentioned before, SymPy is trying really hard to make these values exact. So it's refusing to divide out kind of square root values in the surd or whatever. Now you can make this a little bit more kind of engineering friendly by using this function called sympy.n, and that'll at least kind of divide out and simplify, and you'll see that you've got 70.0 and so on over here. But it's still kind of saying e to the quarter, because it says, well, you know, like I can't even get a proper exact value for that. So what is a man to do? I need therefore to kind of substitute a particular value for time. So let's see what the value of that expression is at time. And because this is now a function where there is no symbols, I can call float on that, and that will, or I can call float on it after I've made it a number, and that should give me a value. Yeah, this is exactly why I've got the evaluate function. Let me just show you what that actually looks like. So the issue here is this Heaviside function that kind of is still hanging out over there. Now, a simple version of what I would like to do to get rid of that is to do subs, and I can actually do, and that'll give me the ability to get a floating point version of that. Now, because that is something that kind of arises a lot when we're doing discrete sampling, this is why I wrote this function called tbcontrol symbolic evaluate at times. Now, that's exactly what it does. It literally only does the simple substitution of the Heaviside so that we don't get that Heaviside in there. And it evaluates that expression at those times. And so in order to get those sampled times, now I have a list of sampled values. These values. Now you can see this actually even still contains all of those nasty gammas. But I'm not worried. These values work fine for what I'm trying to do, which is just to get a plotted value. If you did want a actual engineering kind of value, you could just convert all of that to float. So you can do something like float v for v. So there you have the actual values, and you can kind of see from inspection that the maximum value that we get to is 80.7. Okay, so there you get the answer. But you also see that we know this is the correct analytic value, and this is the same as this diagram that I was drawing over here, right? So we know now that we get to all the way up to there and then start going down. We know that the maximum is over there. Just as a kind of a shout out to kind of future exam questions, it is maybe quite interesting to ask a question like, what would be the maximum temperature of the sampled signal if I sampled at some lower rate, and in other words, I didn't actually sample on that exact maximum, or if I had a second order function and the maximum occurred after the signal started going down. Be aware that you don't, and I'm just warning people because I've seen this before. A lot of people are looking through this and like remembering, oh, the maximum happens at the point at which the step comes down. Now that is true, but only for this particular combination of cases. And it's one of the pitfalls a little bit later that I'm going to go through as well. Now we have numeric simulation. And so the idea is that numeric simulation is going to be slightly easier. Again, I'm going to be using BlockSim, but honestly, this problem was relatively simple to simulate using your own for loop as well. I'm just building a transfer function that represents that sampler signal over there. You can see that I'm using, and again, let me just give a little bit of context here. So remember how these BlockSim LTI blocks work, that we pass in a name. The name of the input is T, the name of the output is Tm. I've got a numerator and denominator polynomial. The time constant, or the coefficient of the top polynomial is just 1. The coefficient of the bottom top polynomial is 8 and 1. And then remember that these LTI blocks have built-in delay handling. So if I just add in a delay of 2, that effectively has that exponential for me as well. I've defined temperature as a function, which just looks at the blocks over here. And when we simulate this, lots of questions was about like, how do I handle this case? This is a block diagram, but it doesn't have any sums. That is what an empty dictionary looks like. So normally there would be a dictionary which contains something like this. Normally there would be something that shows like the output as a function of the inputs. If there are no sums, you just pass an empty dictionary. It's the same as having something like an empty list. You could theoretically, I think, do a diagram without any blocks. I think it won't break, but it may like not have any really sensible results. And then we've got the inputs. Again, I've got a lot of questions. I did have a lot of questions about what is the difference between doing something like this and using lambda. Now, I may have mentioned this in the past, but we have defined something like a lambda. We could do something like what 0 if t is less than 10, else 15. So we could kind of follow using this kind of inline if structure. We could define lambda here, but remember the shortcomings of lambda is that lambda doesn't have the ability to do statements. So you can't actually have an if statement. This is an if expression, which has completely different syntax. So you can only do expressions in lambda. And so to me, I would rather always, usually I will avoid lambda if I can and just use this. This function, also notice that I'm passing in the name of the function, right? A lot of people think of a function as being like name t of t, like this. The problem with this is if t does not exist, or like even worse, I think in this case, t was still the time, the symbolic time, there's going to be lots of weird stuff happening over here. So we just pass the actual function and Bloxham actually runs it. And so in the same way, we can see here's the simulated value of the continuous time, and we can see that the simulation in this case is very accurate, and it lies exactly on. Now, what if I actually wanted to have exactly the values at the time periods, and if I didn't have the sample values available earlier, I could use scipy.interp, or actually numpy.import. So if I do import numpy, so remember that numpy.interp, this is exactly what numpy.interp does, right? It says I've got some kind of smooth signal where I've got known x values and known function values, like I have here, and I want at some particular values. And so remember, we've got this t sampled. These are where the samples are, and so we can interpolate on the smooth t and tm the equivalent numbers that we saw in the previous value, right? So now I'm just looking for those particular values. Then lastly, this is the part that I think is the most confusing, is the Z transform version. And here's where I'm going to kind of draw a little bit of a further picture, because I think I've cracked how to explain what is going on here finally. There is no Z transform that corresponds to this part, or let's say there's no transfer function that corresponds to this part of the block diagram. And the way that I know that is that there are no samplers in that region. Okay, so what we have is Tm is a continuous signal, and there was never any sampling. And so technically the solution that I have here calculates the Z transform of Tm star by using the analytic response of the system. And so what you'll notice is in the way that I'm doing this, I am actually not multiplying. There's no TZ in the correct version of the Z transform solution, right? So why that is the case, and so I want to refer to the data sheet again. And I want to kind of make it clear again what is written in this data sheet when we're talking about the Z transform. And the way that I've come across, or the way that I've thought about explaining this, is to say that when you are working with the Z transform, you should always draw a block diagram to give you the equivalence, okay? So if you have just this, in other words, you only have, that's your entire block diagram, is a signal of time, right? The G of Z or F of Z that is documented in the table, this is the datasheet table, right? This is what the datasheet table does, is it tells you what the Z transform of the sample values of that signal of time was. Okay, so this is basically saying there's a function of time, there's a function of z, and what that means is I've taken whatever that function was, I've sampled it, and now I have, let me draw some kind of representation here. Now I have those values sampled at those points, and I have a corresponding Z transform, and that's what's in the table, right? So in other words, this tells me that if I have something like a unit step over here, then I can get the sampled values at that time. And now, so what this means is that in a very strong sense, if I'm inverting, so if I'm going in that direction, I'm just looking in the table at this function and I'm finding that Z transform. Remember that the inverse transform doesn't actually give me the function, it gives me the dots, right? And so when I invert that transform by evaluating it, remember that that is actually equal to 1 plus 1 times z to the minus 1 plus 1 times z to the minus 2, and so on, right? And these coefficients are what the inversion form actually involve. Okay, the data sheet corresponds to this picture. Now, it also corresponds, you may be tempted to look at the middle column of the table as well, right? But if I have a g of s, remember that I can do the Laplace transform to get to g of s. I can do the inverse Laplace transform to get to g of to f of t. Let me rather do this as t, right? And what we actually have here is a completely reversible process. In other words, if you give me f of t, I can get f of s. If you give me f of s, I can get back to f of t, and I can do that infinitely forever, right? If you give me f of t, when I sample it, because there's a sampler over there, when I get back, remember, I only get these dots. Okay? And so that's the first important point, is that this does not represent the same thing. It's there's kind of, I've always recommended that people draw some kind of a line over here, because the relationship on this table between the Laplace transform and the time domain is not the same as the Z transform in the time domain. How do we then, if we wanted something like a Laplace transform of a transfer function, how would that work? Well, you can get something like the Laplace transform of a transfer function out of this table if you remember that these things on the left are actually also called impulse responses. And so if I sample and I've got a f of s over here, and I sample over there, remember that if I take f of s and calculate the impulse response, in other words, I multiply by Dirac delta of s, which is 1, right? And I inverse Laplace that, I get that same function of time. And because this sampler is introducing these little impulses, it's equivalent to saying, well, I'm actually getting the impulse response of f of s. So in this sense, the data sheet have these two block diagrams representations. Then there is table 17.1, and I hope now things are going to suddenly become clear. 17.1 corresponds to this diagram, right? So the f of s in 17.1 and the f of z in 17.1 is built around the idea that we are taking a sampled section and we're placing that zero order hold in that position. Now, the reason why that's so useful in the textbook is obviously because that's the shape that we often find with digital control, right? So if we have some controller of Z emitting a sampled signal, we're going to have to hold that signal before we put that into a plant. And the signal is going to be read back in a sampled fashion, right? So this piece that we have here, when we're trying to calculate closed loop block diagrams, is exactly the kind of thing that we need. So in the cases where you have a discrete controller with a hold element and a system, table 17.1 gives you exactly what you need. So it saves you a couple of steps, because you could obviously use the data sheet as well. And like, I just want to show you that that's the approach that I've followed in almost all of my notebooks, is that I have used the table in this way because I have this translation over here, right? So notice when I write Z like this, I'm using the data sheet. And I'm saying, well, to get from the data sheet the correct Z transform, the thing that is in that position, look at the similarity here. In order to get this thing, right, where I've got samplers on both sides of a continuous system, that continuous system is the hold element and this f of s, right? So when you walk through this, it means that I can then find this f of z in the table. I can find out what that value is. And the reason why I'm doing that is just to save a little bit of time. I could have actually gone and tried to find this in the table, but what we'll notice is that this structure with the e to the whatever s is not in the table, right? So when we actually look at the table, we see the table only contains all of these relatively simple transfer functions, right? So we can see, okay, there's a s or whatever. We don't see that structure in the table. So we need more work to get to something where we can say, oh, this is f of z, this g of s over s, that typically is in the table. So for instance, here's this, that form for a first order function, where I've got a first order function divided by s, and that's the kind of thing that we're typically looking for in g of s. So hopefully this has uncovered like the mechanics of that. Now, what does that mean in terms of actually solving 17.8 using the Z transform? Is I'm looking in the table at that first order divided by an integrator version of the table, right? So I'm looking at that element in order to find the Z transform. Because we've got a step, we've got another step, we've got a step up, we've got a step down, and we are trying to calculate the Z transform of the sampled value of the step response of the system, right? And so that is what we have. That's the first order system step response. Now, what we need to do is figure out what the coefficients are. So we just have to divide above and below the line by 8 to get the thing in the correct form. We evaluate B, and now we look at that Z transform over there. We also multiply by another Z because we are accounting for time delay. So we have 15, which is the size of the pulse. We've got the delay in the measurement, and then we've got this f of z, that's the step response, and then that's the negative of the delayed step response. And we're delaying that delayed step response by 5 time periods, because, or by 5 time sampling periods, because the step is 10 wide. Let's just get back here. So the step is 10 wide, and we are sampling at 2 seconds. And so that 10 wide sampled at 2 seconds gives us -5. Okay, so now by using the Z transform, I now have an expression. Now, I want you to notice in the correct version of this, I have not multiplied a Z domain input by a Z domain transfer function in the completion of this question, because in my mind, there is no Z domain input. And you get these answers. Okay. Now, I've also just gone through this and said, we can also use table 17.1, right? I've labeled this an incorrect method, even though it produces the correct results, because of the fact that this does not work for any kind of input. So this system, if you said, well, what I'm going to do is I'm going to find the Z transform of a sampled version of this, right? I'm going to push that through a discrete transfer function, which I'll get from table 17.1. In that case, the diagram now looks like this. Sorry, here's one that I prepared earlier, right? So you may recognize this from Slack. The actual signal, right? This is what is actually happening. This is the sketch that we had earlier, right? But you can pretend that I'm going to sample and hold that signal, right? And then obtain, and so in the true facts of the matter, there is never a sample value of the actual temperature. But if we pretend that there is, that's what we're doing if we are finding a U of Z. If we're doing this step, okay, that's what we're doing, because we're pretending that we know that there's some sample value of T. We then hold that, send it to the transfer function, and we then sample the output. In this particular case, the answers are correct. And the reason why that is so is because T is this signal, the reconstructed signal, is the same as the original T. So in this particular case, and this will be the case, whenever T is piecewise constant and sampled exactly at the sampling periods, right, this approach will work. And I mean, it will be numerically correct, because the reconstructed signal will be exactly the same as the original signal, okay? What happens, though, if I have some other kind of input signal, like ramps? In that case, the reconstructed signal will still resemble blocks. And in that case, the answer will be different. So in my opinion, the conceptual application here is incorrect. So unless you actually told me, I know what I'm doing, I'm making this approximation with open eyes, this approach is incorrect and it will not work. So you would be able to do the exact same method that I did for the correct version of the symbolics, right? Find the temperature response and then sample that temperature response at the sampling points to solve this problem analytically, and you'd get the right answer. You do the samples, you'd get the right answer. But if you did it using table 17.1, in the case of non-piecewise constant input signals, that will not work. Beatrix, has that answered your question? Yes, great. And then the last incorrect method, and this one is kind of incorrect for obvious reasons. When I say obvious, like it's obvious that it's wrong in the sense that you see that the values are incorrect. Here I have used the ever popular, but much reviled by me, backward difference approximation. I think a lot of people see this formula, and I'm going to write the formula in the form that it is in the book, to highlight the fact that it is not an equality. The book doesn't say that it is. I have been very negative about using this formula on many occasions. I can tell you that it is almost never what you want. It is the kind of last resort. But this is equation 17.53 in the book, 1 minus z to the minus 1 over delta t. Right, so this is backward difference. And there are a lot of people who look at this and like, they just cannot look away, because they're saying, this seems like exactly the kind of solution that I like, right? It's a plug and play solution. I have a transfer function which has lots of S's. I'm looking for something that has lots of Z's. Plug and play solution is I plug this in. But what we can see is that this is straight up incorrect. In other words, it is an approximation. So you can clearly see in this response over here that we do not in fact recover the correct signal. We don't even, like, you can play around with shifting this around, but like it's a fool's errand. They are approximately the same, but they are not the same. And so the very incorrect version of this problem is to use backward differences. Now, once you've snapped this, once you understand like what these block diagram equivalents of the tables mean, and I think this is kind of, I was quite excited when I came across this idea that as long as you kind of sketch the block diagram equivalents, the differences become very clear. In other words, you use the data sheet to solve this kind of problem. In other words, I have a continuous signal and I want the sampled equivalent, right? Or I want the sampled version of that. Or I have a continuous signal with samplers on both sides, and that's all I have. I don't have any other stuff. Like I just have f of s, I've got samples over there. Then you use the table in the datasheet. Only if you have this situation, where you have a sampler, a hold element, a function of z, and another hold element, under those conditions, you can get the answer to that. That is what is in table 17.1. The rest of the math in discrete is exactly the same as continuous. And so solving for a controller in the direct synthesis method or manipulating these transfer functions works exactly the same way. But people get confused because they don't correctly understand what these different tables mean and how the Z transform is applied. So hopefully this lecture has clarified that.